Hello, my name is Ahmet Monesnov of Cukurova University Computer Engineering Department. Today I'm going to talk about Radial basis function neural algorithm and perform a simple test code on Python using three different datasets to test results. Radial basis function networks, or RBF nets, are used for such a scenario, regression or function approximation. We have some data that represents an underlying trend or function, and we want to model it. RBF nets can learn approximate the underlying trend using many Gaussian bell curves. An RBF net is similar to a two-layer network. We have an input that fully connected to a hidden layer, then we take output of the hidden layer, perform and weighted sum to get our output. Inside the hidden layer, there is a Gaussian RBF, and this differentiates an RBF net from a regular neural network. We are using an RBF as our activation function, more specifically a Gaussian RBF. In this figure, the Gaussians have different colors and are weighted differently. When we take the sum, we get continuous function. To do this, we need to know where to place the Gaussian centers and their standard deviations. We are going to use K-means clustering to determine the centers for each of the radial basis functions. In this code, we implement the K-means clustering algorithm to compute the standard deviations. If there is a cluster with none or one assigned points to it, we simply average the standard deviation of the other clusters. Because we can't compute standard deviation with no data points, and standard deviation of a single data point is 0. I'm not gonna explain the K-means clustering in this video because I explained it in the other video. So I'm gonna pass this part. Here we created the real heart of the RBF by creating a class. Here we have option for number of bases, learning rate, number of approaches, which RBF to use, and if you want to use the standard deviations from K-means, we also initialize the weights and bias. Keep in mind that RBFNet is modified two-layer network. So there is only one weight vector and a single bias at the output node. Since we are approximating a 1D function, specifically one output. In fit function, we are computing our weights and biases. In the first few lines, we either use standard deviations from modified K-means algorithm, or we force all bases to use the same standard deviation computed from the formula. The rest is similar to propagation, where we propagate our input going forward and update our weights going backward. And here our predict function. In this section, where the program starts, we used a sinus function to generate our data. Then we added some uniform noise to it. Let's run a test and see the result. From this result, we can notice that our RBFNet performed pretty well. Let's make some changes to the dataset and test it again. For example, let's generate the same values from cosine function. This time, as we can notice, the result is not that much perfect. So let's play around the basis value. Let's give it the number 4 and try again. Now we can notice that the result is a bit better than before. Now let's use our previous dataset, which contains the number of hours and the student score. To do this, I'm gonna change this part. Let's run the program by uncommenting this line. You can notice from the losses that we have really high values. So before I get the graph, I can expect that I won't have a very good result. As I expected, this method is not suitable for this kind of protection. These codes are available again in the comment section.